Let's take a look at these probability practice problems. So in this first problem, you're given information in the form of a two-way table about a survey of 30 students. And again, a two-way table is appropriate when you've used two different ways of dividing a group of subjects, whatever the subjects may be. In this case, we divided them by whether they're right or left eye dominant, and then whether they're right-handed or left-handed. And so we have four different categories. We have right-handed and right-hand dominant. These 14 right-handed, left eye dominant, these 11, etc. So these four boxes add up to 30, which is the number of students in the survey. But we want to add the total columns and the total row so that we can do additional calculations. So we sum the rows, we sum the the columns. All right, so when we're asked what is the probability that a randomly selected student will be right-handed under the condition that they are right-hand dominant? In other words, looking only at right-hand dominant students, what's the probability that if we pick one at random, they'll be right-handed? And so we look only at the right eye dominant students, the 17. The probability that one is right-handed would be 14 out of 17, or 0.823. Then we ask the same thing, but we reverse. We say, what about the probability that a randomly selected student who is right-handed will be right eye dominant? So now we look only at the right-handed students, these 25. Out of those, 14 are right eye dominant, and so that gives us 14 out of 25, or 0.56. And again, in this symbol here with this probability in the vertical bar, this is a conditional probability, and the group to the right of the vertical bar tells us the group we're using to select from, and so that'll provide the denominator, in this case 17, in this case 25. Okay, now we have what is the probability that a student is right eye dominant or right-handed? Well, now we're talking about picking a student out of the entire group of 30. And we look at right eye dominant or right-handed, and it's all the people in this column here and all the people in this row here. So it would be the 11, the 14, and the 3, which sum together, 11 plus 14 plus 3 gives us 28. We could also say it's this column minus this row, but then we have to subtract the 14 because it's being counted twice. Once is in this row and once in this column. So we have 17 plus 25 minus 14, which also gives us 28. Or we could say it's everybody except these people right here. And so it would be 30 minus 2 over 30, which again gives us 28 over 30. What's the probability being left-handed and left-eye dominant? Well, that would be just this group of people right here, because they have to be now both in this row or this column and in this row here. So that would be just 2 out of 30. And then notice that these two are complements of each other. In other words, this probability here in E is 1 minus the probability in D, and obviously vice versa. Okay, so then we wanted to construct a tree diagram to represent the situation, and it's not clear what we would necessarily use as the first level, so we just said, all right, let's use handedness as the first level. So I divided it into two different tree diagrams. One, I have the numbers where I have 25 right-handed and 5 left-handed. And off of that, 14 of the 25 are right eye dominant, and 11 of the 25 are left eye dominant over here. It's 3 out of 5 are right eye dominant, 2 out of 5 are left eye dominant. So when we multiply down here, we get these numbers down here. So these numbers are the 4 numbers in the inner boxes here. 1, 2, 3, 4. And then we had to calculate these probabilities. And over here, all we did was say, well, all right, 0.83 or 83% of the 30 students are right-handed, and the remaining 17% rounded are left-handed, and that's just 25 over 30 and 5 over 30. And here, these probabilities are just these fractions converted to decimals. So you have a 0.56 probability of being right-eye dominant if you're right-handed, and you have a 0.6 probability of being right-eye dominant if you're left-handed, according to our statistics. And so then we multiply these down, And really all of these numbers here in this right-hand tree at the bottom level are just the numbers in the left-hand tree at the bottom divided by 30. 14 over 30 is 0.47, 11 over 30 is 0.37, etc. All right, so now we have a more descriptive situation where we're to construct a two-way table. So this agriculturalist takes 50 samples of soil and measures two things, the nitrogen and the phosphorus. In each case, you're going to either have low or high levels, and so it's going to be set up for a two-way table where we have either the columns or the rows will be nitrogen, and then the phosphorus will be the other. And they give us some values here. So we're going to just pick nitrogen to be the column headings, and the row headings will be phosphorus. We could have done it the other way around. And so what we know is that 46% of the sample is low nitrogen, which means that the remaining 54% would be normal or high nitrogen. And for the phosphorus, we were told that 28% was low, and so that gives us the remaining 72% would be normal or high. And we also know that 10% were both low nitrogen and low phosphorus. So once I have these values, the row and column totals plus this 10, I can calculate everything else. So I have the 10 here, so that means that this 28 minus 10 would be 18, and I can just calculate everything. In the parentheses here, I have, instead of the percentages, the actual numbers of samples. So 10% of the sample of 50 is 5 samples, 36% of the 50 is 18 samples, etc. Okay, so now we're again interpreting these probability expressions. So we have, what's the probability that a randomly selected sample is low in nitrogen and low in phosphorus? So that would just be the 10% over the 100% or the 5 over 50. Either one is going to give you 0.1. What's the probability that a sample will be low in nitrogen given that it's low in phosphorus? So looking only at the low phosphorus samples, which are 28, what's the probability that if I pick one at random, it's going to be also low in nitrogen? That would be 10 out of 28, or 0.357. And again, low in phosphorus here means that that gives us our denominator. And so that would just be these 28 here, which are the 28 out of the 50 that are low in phosphorus. Okay, calculate the probability that if you're not low in phosphorus, you are low in nitrogen. So now we're looking at this column here, this row here. So that would be the 72%, and out of those, 36 would be low in nitrogen. So we have 36 over 72 is 0.5, or we could have done 18 over 36, which is also 0.5. Okay, are nitrogen level and phosphorus level independent? And what that means is, are you more likely to be low nitrogen if you're low in phosphorus, or is it the same whether you're low in phosphorus or not? And what we can see here is that 10 out of the 28 are low nitrogen when they're low phosphorus, and we said that was 35.7%, but 50% are low nitrogen if they have normal or high phosphorus. So in other words, if I know the phosphorus level, I can make a better prediction about the nitrogen level. So it actually matters in terms of predicting the nitrogen level. It matters whether the phosphorus level is low or high. And that means that these two are not independent. If they were independent, then the percentage of low in this row here would be the same as in this row here. It wouldn't matter whether you were normal or high phosphorus. That wouldn't have any impact on whether you were low or high nitrogen. Okay. All right, constructing a tree diagram from this situation. So a spam filter correctly identified 90% of actual spam and correctly identified 90% of legitimate email as legitimate. At that time, 30% of email was believed to be spam. So at our first level, we're going to have spam, no spam, and that would be 0.3 spam, 0.7 legitimate email. We said that if it's spam, it's 90% likely to be identified as spam. We'll call that a positive result. And so that means we would have a 0.9 here. When we multiply down, we'd have 0.27. And that means if it's 90% positive, it's going to be 10% negative. And so again, we multiply down. Whereas for the legitimate email, you are 95% likely to get a negative result if it's legitimate email. So we have 0.95, and therefore this positive result would be 0.05. By the way, this would be a true positive here. This would be a false negative. This would be a false positive, and this would be a true negative. Okay, so again, let's evaluate these probabilities. The probability that if it's identified as spam, it really is spam. So we look at the two positive results. That's where it was identified as spam. That the sum of these two will be our denominator, so 0.27 plus 0.035, which gives us 0.305. The numerator then would be, out of those, just the ones that are tested as positive. And then for the next one, it's what's the probability that if it's identified as legitimate email, it actually is legitimate email. And so we take all the negative results where it's identified therefore as legitimate email, and we add those together, so we get 0.665 plus 0.03, and that gives us our denominator of 0.695. The numerator then is just the legitimate email of 0.665. So it turns out that if it's identified as legitimate email, there's a 0.957 probability that it is legitimate email. Probability that it is spam or identified as spam would be both of these categories, which are spam, plus this where it's identified as spam. So we would sum those three and get 0.335, or we could just subtract this 0.665 from 1. Both of those give us 0.335. Okay, so here we start out with set A, which is the set of all letters in the alphabet. Set B is the letters A, B, C, D, E, F, G, and set C is the set of all letters that appear in the word giraffe. So those would be the letters A, E, F, G, I, R. Notice, again, we only list letters once. We do not list the F twice because it appears twice. Okay, what is B union C? So this enlarged U here represents union, and it is the set of all elements that either in B or in C. So it's equivalent to OR. And so it would be all of B plus the things in C that are not already in B. So those would be the I and the R. So we have A, B, C, D, E, F, G plus an I plus an R. B intersection C would be only those letters that appear in both sets. So that would be the A, the E, the F, and the G. So that is our intersection, and that's equivalent to an AND. Okay, the probability that a randomly selected letter from S will be in the set B complement. So our denominator is going to be 26 because that's the size of set S, which is a set of all letters. That should actually say set A. And B complement is all the letters that are in A but that are not in B. And so that would be, since B was A through G, that would be H through Z. And so since there are 7 letters in B, there'll be 19 letters in B complement. So therefore the probability would be 19 over 26. Okay, how many letters are in the set B complement intersects C complement? So this would be all the letters that don't appear in B and don't appear in C. And so when we look at that, we have, this is really all the, this is the complement of the union of sets B and C. In other words, take all the letters that are in B or C and then take the complement of that. And so since the union of B and C contains 17 letters, then I'm sorry, the union of B and C contains 9 letters, and that's what we got up here in A. Then the complement of that is the remaining 17 letters out of the 26 in the alphabet. So it's 17. So we're constructing a Venn diagram here, and we're saying that this entire rectangle contains every letter in the alphabet, all 26. The first circle over here would be the set that we designated B, and it's got A, B, C, D, E, F, G. The second circle would be all the letters that appear in the word giraffe, and that would be A, E, F, G, I, and this G should be an R here. In between, in the overlap of these two circles, would be the intersection, and so that would be the letters A, E, F, and G. And then outside of either circle would be the letters that appear in neither set B nor set C. Okay, number 5. So you're to evaluate these probabilities. So the first is the probability of rolling a multiple of 3 twice in a row when rolling a 6-sided die. So the only multiples of 3 that appear on this 6-sided die are 3 and 6. And so that means you have a 2 out of a 6 chance of rolling either a 3 or a 6. The probability of doing that 2 times in a row would be 2 over 6 times 2 over 6, which is equal to 4 over 36, or 1/9, or 0.111. Okay, in B, we have this spinner that's been divided into 8 sections of equal size. When we spin the spinner, the probability that the spinner will land in any of these sections is proportional to the size of that section. So it's going to be a 1/8 chance of landing in any of these sections, since they're all equal size. So then we're asked, what's the probability that it's going to land in a slot with solid color 3 times in a row? Well, there are 3 of these wedges with solid colors, so the probability of landing in one of them would be 3 out of 8. When we spin it again, the probability is still going to be 3 out of 8. It doesn't change. And then when we do it a third time, it again remains 3 out of 8. So the overall probability is 3/8 times 3/8 times 3/8, which is equal to 27 over 512, or as a decimal, 0.053. Then we're asked the probability of pulling 2 socks of different colors from a drawer with 3 blue and 3 red socks. So you can do this with a tree, you can do this without a tree. So I set it up with a tree here, and I said the probability of pulling a blue sock or a red sock when you pull out the first sock would be 3/6 for each. But then after you've pulled out the blue sock, you would have only 2 left that are blue out of the 5 that are remaining, so the probability of pulling another blue sock would be 2 out of 5. And again, this is sampling without replacement. Once we take that first sock out, it stays out. And so then we would have, if we pull out a blue sock, we'd have a 3/5 chance of pulling out a red sock for the second. On the other hand, if we pulled out a red sock first, we'd have a 3/5 chance of pulling a blue sock out after that, or a 2/5 chance of pulling another red sock. When we multiply down here, we get all these possibilities: blue, 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 red, red, blue, and red, red. And we multiply out, and we get these 4 possibilities. And when we add them together, we're going to get 30 out of 30, because these are the only 4 possible outcomes. The probability of getting 2 socks of different colors then would be 9 out of 30 if you got blue and red, and 9 out of 30 again if you got red then blue, and the sum of those would be 18 out of 30, or 3/5. So you could also just say, well, the probability of pulling a blue then a red is 3/6 times 3/5, or 9/30, and the probability of pulling a red then a blue would also be 3/6 times 3/5, so another 9 out of 30, and again you would sum those. This way is fine as long as you have correctly identified all the different ways that you could pull 2 socks of different colors, because there would be the way of doing it, pulling a red then a blue, and a second way of pulling a blue then a red. If we wanted to figure out how many ways are there to pull 3 socks, well, then we get a much larger set of possible outcomes. Okay, determining if events are independent or dependent. And so what we want to know is, does what happens in the first event have any effect or provide us with any greater ability to predict what happens in the second event? Rolls of a die is in 5A here. When I roll the first die, it has 0 impact on what happens when I roll the die again. So those 2 are independent. On the other hand, for the socks, when I pull out by the way, the spinner also independent, because there's going to be 3/8 probability on the first spin, 3/8 on the second, 3/8 on the third, and it would always be 3/8. It wouldn't matter what happened the first, the second, the third spin, etc. With the socks, on the other hand, you can see that if I pull a blue sock out, my chances on the first pull, my chance of pulling a blue sock out on the second would be 2/5. On the other hand, if I pull a red sock out, my chances of pulling a blue sock out as the second would be 3/5. So because these probabilities are different from these, in that, blue here is 2/5, here is 3/5, these are dependent. What happens with the first pull has an impact on what happens with the second. Or if it has no actual causal impact, if it allows us to make a better prediction about what will happen in the second event, then they're not independent. Only when these conditional probabilities on both or all three or however many branches you have, when this set is identical to this set, then you have true independence. Now in this case, even though we have 3/5 and 2/5, the blue is different from this side to this side. So these are considered to be dependent. Okay. Some challenge problems. So Shannon has 3 coins with different probabilities of landing heads up. Coin A is 1 out of 10, B is 2 out of 10, coin C is 3 out of 10. If she flips all 3, what is the probability that at least one coin will land heads up? Okay. So here we list out all 8 possible outcomes. Heads, 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 tails, heads, tails, heads, tails, heads, heads, etc. And then we just do the multiplication of the probabilities. 0.1, 0.2, 0.3 to get heads, heads, heads would give us 0.006. On the other hand, heads, heads, and then coin C tails would be 0.1 times 0.2, but now 0.7 for coin C because there's a 1 minus 0.3 or 0.7 probability that coin C will land tails up. So we then go through and do this whole thing, and the probability that at least one coin will land heads up includes the first 7 of these. In all of these, there's at least one head. And so if we sum all of these, we end up getting 0.496. Now, obviously, it would be easier to say, well, the only one that doesn't have a heads would be this one. And so we could just calculate this one probability of coin A going tails up, coin B, and coin C, which would just be the product of those 3. 0.9 chance that coin A lands tails up, 0.8 that coin B does, 0.7 that coin C does. Multiply them, get 0.504. And then we would subtract that from 1 to get the remaining possibilities here. Okay, Tristan and Isolde are playing a dice game where each player rolls a single 10-sided die with the numbers 1 to 10 on the sides. Players keep track of their overall scores and adding them up, and whoever has the highest score after 10 rounds is the winner. Going to the last round, each player has one more roll. Isolde is leading by 5 points. So what's the probability that Tristan can overtake her and win or tie the game? Well, there are a total of 10 times 10 different possible combinations. So it could be like a 1 and a 1, a 1 and a 2, a 1 and a 3, all the way up to a 1 and a 10, or a 2 and a 1, a 2 and a 2, a 2 and a 3, etc. So there's 10 times 10, 100 possible combinations of the 2 player scores. So we just looked at, first of all, if Isolde rolls a 7 or higher, a 6 or higher, Tristan cannot win because he can't make up a 5-point deficit if Isolde rolls a 6 because the highest he can get is a 10, and so he would only gain 4 points on her. He can, however, win or tie if she rolls a 1, 2, 3, 4, or 5. If Isolde rolls a 1, Tristan can beat or tie that score by rolling either a 6, a 7, an 8, a 9, or a 10. If, on the other hand, she rolls a 2, he can beat it with a 7, 8, 9, or 10, etc. And so when we look at all these possible ways that you can win, it should be 5 plus 4 plus 3 plus 2 plus 1. So this is actually wrong here. So it should be 15. And we'll change that. And so the probability would be 15 out of 100, or 0.150. Okay. I'm not going to go over the harder challenge. Read it if you want, and ask me questions if you have any.